Hello everyone, we are going to do this exercise about the Striling cycle. In this exercise, the first step is to talk about the Clapeyron diagram that is given now, because most of the time in the exercises, the Clapeyron diagram is not given, and then we ask you to do it. But in this exercise, it's given, and then you have to understand what is the nature of the cycle by doing the analysis of the Clapeyron diagram. So we are going to answer the first question here. And then for the next questions, it will be more about the work, about the heat, and about the comparison of what is going on for every single transformation. And in the last question, we are going to calculate the efficiency of this thermal machine. Okay, so let's start with the first question. So I'm just going to make again the diagram so that we can make the analysis of it. So we have PV Clapeyron diagram. So this cycle is composed by 4 steps. 2 of them are isothermal and 2 of them are isochoric. The first state is the state A, and we start here, and then we have an isothermal transformation where the volume is decreasing. So we have this step. Here is the state A. Here is the state B. Then we have an isochoric step, so the volume is constant, and isochoric curve is a vertical straight line in the PV diagram. So this is the second transformation until the state C. And then we got another isothermal transformation, and we come back to the initial volume here. So we are until the state G. And then the last step is an isochoric transformation where we come back to the initial state. Of course, it's a cycle, so the final state is the same than the initial state. Okay, so this is given by the wording. And what is interesting here is the fact that we have already the sense of evolution of the cycle. So if we have that, then we are going to able to tell if it's a motor cycle or if it is a receptor cycle. I'm just going to make it because it has been erased. Okay, so we know that if the sense of the arrows are in the clockwise sense, it means that this is motor cycle. So what are the characteristics of a motor cycle? The sense is clockwise and the total work of the cycle is negative. So this is what we are going to answer for the first question. Is clockwise, which means that it is a motor cycle. So what's the definition of a motor cycle again? A motor cycle means that your system is at the end of the process, so I'm talking about the resultant work, the summation of every single work for every single transformation. If you do the summation of all of them, then you will have the resultant work that is called W cycle. and this resultant work is negative. So the sense behind this is the fact that if you have a system that is providing to the outside some mechanical energy, then the work is negative. Imagine that you are an operator that is in the outside. So you are in the environment and you are external to the cycle. And you are going to take the energy, the mechanical energy that the system is creating. So in your referential as operator, the mechanical energy is received, but in the referential of the system, the mechanical energy is given away to you, right? So the system is going to have a mechanical energy that is negative because it's getting out. So that's the reason why for a motorcycle, W system is always negative. So that is the sense of a motorcycle. So for you as operator, it's going to be positive, obviously, but for the cycle, it's negative. Okay. So I'm just going to write a sentence about the physical sense behind this. I can add some an information that is not requested here, but that is interesting. If you come back to the graph, so by definition, the work, if you are wondering what is the work for every single step, for example, let's take the step AB. The work is the area that is between your curve and the abscissa. So this is work. If you take this area, so this is just a remark. This represents the work of the step BA. So that is the work AB, sorry, because we start at A, obviously. And then if you want to know, I mean, this process works for every single curve in general. This is a general process. For example, if you want to know what is the work of the specific transformation CB, then you have to take the curve CB and take the area between CB and the abscissa. So if you do that, it will be this area. So the red lines will be the area that represents the work CB, CG. And then for the transformations BC and GA, if you want to represent the area behind below the curve, there is no area because it's a straight line. So if it's a straight line, there is no area between the line and the abscissa. So what is the reason for that? Because these two transformations are isochoric transformations. So if it's an isochoric transformation, then the volume is constant. And if you go check out the video about the isochoric transformation, the work is always 0 for an isochoric transformation by definition. So it makes sense here that you have 0 area because this is the work that is worth 0 actually. So it makes sense. So now let's come back to the questions. Now let's do the second question. The second question is, in the second question, we want to prove the fact that the heat that is given away, so by the system to the outside during the GA transformation is the same that the heat that is received by the system during the transformation BC. So this is what we want to prove here. So if I translate this in terms of equation, it means that QDA is equal to minus QBC, or QBC equals to minus QDA, same thing. So question 2. So if I will remember the wording, it was demonstrate the fact that the heat that is received between B and C states is the heat that is given away between G and A states. You can go check out the question, but this is what I think was the question. So BC equals to minus GA. So now what we have to do is to calculate separately everyone and then each one of them, and then just tell that we remark the fact that they are the same at the difference of the sign. So let's calculate GA, the heat at GA. So for this transformation GA, the transformation is isochoric. If we are in isochoric case, then we can use the fact that delta U, so the first law of thermodynamics, is equal to the heat plus the work. So that's the first law. But as we said in the other video, if you go check out, then the work is 0 because it's isochoric, and then it means that delta U is equal to Q, the heat. So that being said, we can check out in the memo that of the formulas of thermodynamics the fact that delta U is equal to CV delta T. So I just need to replace in order to have my heat. So this is also equal to the heat. So now I'm going to specify obviously the fact that we are talking about the step GA. Always do that so that you are not getting confused between the transformations. So QGA is equal to CV TA minus TG. Always final temperature minus initial temperature, never in the other sense. So now if you go check out the wording, TA and TG are actually specified as T2 and T1. So what we are going to do is to replace TA by T2, TG by T1. Another information that we know is the fact that this difference, T2 minus T1, is negative because T1 is higher than T2. So this is negative according to the wording. I really advise you to always give the sign of the heat or the work when you are calculating it. If it's something that you can make easily, then do it, because this is going to help you at the end of the process when you want to calculate the efficiency. The efficiency, as you are going to see at the end of the exercise, is always the ratio of what is your benefit as external operator. So I'm not talking about the system, I'm talking about person that is getting the benefits of the system as a machine. So it's the ratio of the benefits over what the person has to pay to get the benefits. And this is important to know the signs of every single transformation in order to know if, of the heat or the work, in order to know what is the thing that you provide, what is the thing that you receive. So this is important to know the sign. If it's not requested in the question, then you don't have to specify it. But if it's easy for you to specify it, then do it. It's very good, I think, to make it when it doesn't waste your time, when it's easy. So that this is supposed to be a D, not a B. Okay. So let's continue. Then we have to do the heat calculation, but for the step BC this time. I'm just going to add a small remark here. So the fact that the heat is negative, it means that the system is releasing the heat to the outside. Okay, so let's come back to now the new heat calculation. So we want to calculate the heat for BC transformation. First step, check out the nature of BC transformation. So this is again an isochoric transformation, so we'll have to make exactly the same process. So if it's isochoric, then it means again that the heat QBC is equal to CV delta T, the variation of temperature between B and C. So this is equal to CV TC minus TB. So I'm just applying the expression, the general formula. And then again, TC and TB are specified in the wording. TC is T1, TB is T2. So I just need to replace. Okay, so as we said in the beginning, according to the exercise wording, T1 is bigger, is higher than T2. So it means that this difference now is positive. So if we compare both equations that we had, so I'm just going to go here. So if you compare these two equations, I forgot to write the CV. I'm just going to write it now. Here, there's obviously the CV. Okay, so if we compare both equations, this equation and this equation, they're the same at the difference of the sign. So one is CV T2 minus T1, and the other one is CV T1 minus T2. So we just proved the fact that both heats are equal in terms of amount, but are just opposite in terms of what is getting in and what is getting out of the system. Now, what is interesting again is the fact that for the QBC heat, we have a positive value as T1 is higher than T2, and this means that your system is receiving the heat during this step from the external environment. And then we just also need to write the fact that QBC equals to minus QDA is checked, so it works. So this is verified. So we answered the question. Now the next question is to calculate the work and the heat for the two isothermal transformations this time. So let's do that. Because actually now in the first question, we were answering the question will be calculate the work and the heat for the isochoric transformations. There is no work for both, so we calculated the heat. Now for the next question, it's the same thing, but for the isothermal transformations. Because as you remember, this Striling cycle is a succession of only isothermal and isochoric transformations. So let's start with the CD transformation. Isothermal. So first of all, we are going to use the first law of thermodynamics. That says the fact that delta U is equal to W plus Q the heat. But something interesting. So again, you go check out if you want the video about the isothermal case. But something that you have to know is the fact that delta U is equal to 0 for isothermal transformations all the time. So, I mean, if you want the explanation about that, as I said, you can see the other video, but I'm going to be very quick on the reason why it's like that. It's actually related to the interactions of the particles inside of your system in the very small scale, and the temperature is like an indicator about that. So if your temperature is constant, then delta U is constant. Delta U is 0, sorry. Okay, so if we have this equality, then it means that the work is equal to minus the heat. So if I calculate one of them, I have the other. So let's calculate here. We are going to start with the calculation of the work. So what is WCD? I'm going to go from the very general formula of the work, the elementary work, GW equals to minus PdV. So that's the very general formula that works for every single transformations. And now we are going to apply it to the isothermal case. And then in the process, it's going to be specific to the isothermal case. But now it's the general formula. So work WCG equals to the integration of minus PdV from the state C to the state D. So now I need to specify the boundaries. So I specified the state, but I need to specify the physical quantity that I integrate. And here the physical quantity that I integrate is the volume. So the boundaries are going to be V1 and V2. VC and VD, I mean. So now there is something else that we need to do is to replace P by an expression depending on V, as our integration variable here is V. So I'm going to use the perfect gas law for this. And I replace. So I will have integration between, as I said, VC to VD minus nRT over V dV. Okay, so now something interesting is to identify what is constant. So what is constant here? N is a constant. N is the number of moles. R, the constant R is is obviously constant, as we said, and T, the temperature, is also constant. Why? Because it is the isothermal case. So this is constant because it's isothermal. So just because of that, I'm able to take all these things and get them out of the integration. All of this, I'm going to take it outside of my integration, and then I will integrate. So primitive of 1 is the variable itself, so the primitive is going to be V. So I just need to make the difference as a result. Minus nRT. And then I just need to make the difference as the primitive. Just something that I forgot to write here. I think I'm going to make an intermediary step between both, because it's not V, yeah, I forgot to write the 1 over V actually, that's why. There is 1 over V here, so the primitive is ln of V, so we will have here primitive of ln V between VC and VD. So I just need to make the difference now. Minus nRT. As the primitive is ln, I just now make the difference ln of Vd minus ln of Vc. But we said that if we go check out in the wording, actually, we have the values 1 and 2 for every single one, so we can just replace. So in mathematics, again, you can go check out the video about isothermal transformation if you want. I'm not going to specify all the steps, but here I'm allowed to make the ratio instead of the difference, minus nRT ln Vd over Vc. So this is equal to minus according to the wording. If I replace with the information that are given in the exercise, then I can just say that V2 is Vg and Vc is V1. So the ratio V2 over V1 is positive because V2 is higher than V1. So that is positive inside of the brackets. But I have a minus in front of the bracket, so the whole thing is going to be negative. Another mathematical law that I'm going to use here is the fact that when you have minus ln A over B, then this is equal to ln B over A. So I'm just going to apply this law here. And now the whole result is obviously negative, as we were saying earlier. So this whole thing is negative. So if the work is negative during this specific step, be careful. I'm not talking about the resultant work of the whole cycle here. I'm talking about the work just for the step CD. Because if you want to know if your cycle is motor or receptor, as we did in the first question, then you need to know what is the sign of the whole resultant work, which is the summation of every single work of every single step. But here I'm just talking about one step. So during this one step between C and D states, the work is negative. So it means that at this moment, your system is giving away mechanical energy to the outside. So this is the physical sense behind this. And also now, if you remember in the beginning of this process, we were saying, according to the first law of thermodynamics, the fact that the work is equal to minus the heat for this isothermal transformation. So as I calculated the work, I also calculated the heat during the transformation Cg. So I have Q Cg equal to minus W Cg. So the heat is actually positive this time, as it's the opposite. For the Cg transformation, the system is receiving the thermal energy because the heat is obviously related to the thermal energy, and the thermal energy, and gives away, is providing, I'm going to say, okay, so during this transformation, the system is receiving the thermal energy from the outside and providing the mechanical energy to the outside. Now we are going to do the calculation for the second isothermal transformation, which is AB transformation. So it's exactly the same process because it's the same nature of transformations, isothermal. So I'm going to take exactly the same rules. So we have the fact that the work AB worth the opposite of the heat AB. And also we are going to have the same logical process here that you had for the CD transformation. So the work the work is going to be I actually just need to replace the boundaries of my integration, but it's exactly the same process. So finally what you all are going to have is this. Equal to NR. I'm just going to replace the A by the C and the D by the B in my previous result. Or if you want, you can remake the whole process. You can replace it as you want. So WAB is going to be equal to minus NRC ln of VB minus ln A VA. And this is also, as we said, the ratio Okay, now that I know this, I'm going to replace according to the wording the information that we have. So we know that VB is V1 and that VA is V2. So I'm just going to replace this. So it's always the same steps. You have to make the same process, but be careful about two things. The boundaries of your integrations are very important. And also something that is important is when you are going to replace. So in general, in the wording, there are some information that are given about the physical quantities of the work, about the volume, the temperature, the pressure, stuff like that. And you have to identify what are the information that you have, and then just when you are going to replace, you need to replace with the physical things that you know that are given as information in the wording. So in this exercise, the replacement is quite easy because it's just to replace VB, for example, by V1 and stuff like that. But in other exercises, you need to express some physical quantity in function of others. And then the replacement in that cases is very important, and you don't have to make mistakes at this point. So my advice for that is to make notes in the beginning about what you know from the wording and what you can guess easily from the wording by mostly using the perfect gas law, and if it's adiabatic, PV power gamma equal constant. But for now, we just need to replace VB by V1, that's it. So let's do it. So it's going to be V1 over V2. And that is minus the heat. But before, I'm just going to use the mathematical law that allows me to get out the minus and reverse the ratio instead. So this whole thing is positive, as V2 is bigger than V1. Again, we are going to use the fact that the work is equal to minus the heat, as it's isothermal. So the heat, QAB, worth minus the work. And this is going to be negative then. Okay, so what's the physical sense of that? It's the fact that during the AB transformation, my system is receiving mechanical energy from the outside, and it is providing thermal energy to the outside. So it's actually the reverse of the previous transformation in terms of physical sense of what is going on here. So let's make a sense about that. So as you know, the work is always related to mechanical energy and the heat is always related to thermal energy. Okay, so now that we have these informations, my advice is to come back to the Clapeyron diagram before even making the calculation of the efficiency. The next step is to make the calculation of the efficiency, but I recommend you to come back first to the Clapeyron diagram and to represent the information that you just get in terms of what is positive, what is negative for the heat and the work. Why doing this is important? Because when you will calculate your efficiency, this is going to help you to see things better in terms of what is the benefits and what is the thing that the operator provided before. So this is going to help you to know what is positive and what is negative for your system in general. So we're going to represent that here. So during the, actually I think I'm going to make a new diagram because there are already a lot of information in this one with the work area. So let's come back. Okay, I'm going to make the Clapeyron diagram here. We have A, B, C, G, the sense of evolution, that is, I just insist in the fact that it's motor and the clockwise sense is something specific to the motor cycles. Okay, so that was isothermal. That was isochoric. And now we are going to represent what is getting in and what is getting out. So during the step CD, we said that the heat was positive. So the heat in this step was getting inside of your system, and it's positive. So Q, CG, positive. Then during this same transformation, we made the calculation of the work, and we saw that the work was negative. So at this point here, the work is getting outside of your system. So WCG is negative. Now if we look at the step AB, so for the step AB we said that the work was positive, so the system was receiving the mechanical energy from the outside. So if I want to represent that, I will make the arrow getting in and WAB positive. Now if I remember the result that we had for the heat was negative at this point, so the arrow is getting outside and the sign is negative. So this is the resume of what we get for the previous question in terms of signs. Now we are going to make the last question, which is about the efficiency of your system. Okay, at the last question, we want to apply this formula. So the the efficiency, eta. Sometimes it's called eta, sometimes it's called small letter e, depending on the book, for example. So eta is equal to what you get as operator over what you had to pay. So U represents the external operator, not the system. Be careful. Something important when you have such a situation, when you want to calculate the efficiency, the first thing is to define the goal of your machine. For example, you can have the same mechanical process, the same system, but depending on what is the benefits of the person that is the operator, then you have to define an eta that is going to be different, because depending on, for example, if you want to take the heat, your benefit is going to be the hot heat. But if you want to take the cold, for example, for a fridge, then your benefit is going to be the cold. So what is going to be in the equation of eta depends on the definition of your cycle. Here in this example, the cycle is like an engine for a car, for example. So what you provide is the combustion, and what you get as benefit is the mechanical energy, so the work. So in this case, the benefits of the external operator is the work. But be careful, we always take it as absolute value. Why? Because as we said, for a motor cycle, the resultant work is negative in the referential of the system, right? But now for eta, you are in your referential as operator. So you want it to be positive. So you are going to take the absolute value so that you don't have a negative sign involved. So eta is going to be equal. There is another video that explains more details about about how works the efficiency for different cycles, if it's motor or if it's receptor, etc. Depending on what is the benefits that you have in the definition of your machine. So now I'm going to go fast on that. I'm just going to write the equation. So eta is the absolute value of W cycle over what you had to pay, and what you had to pay is the combustion that you made in the beginning of the process, and this is something that is received by the cycle. So this is the heat that is positive for the cycle, so we are going to call it Q received by the cycle. Okay, this is supposed to be cycle. I'm just going to write it again. Anyways, okay, so let's continue. So what is the work? What is the heat received? So this is why it's useful to make the diagram above. So let's come back to the diagram. Here, the work that I'm going to take as a benefit is this one. So it's actually the summation of all the works. So I'm going to take the W cycle, and I will make the summation of all the W's that I have, because this is actually the result of the mechanical energy that is provided finally by the system as resultant one. And then what is the thing that I provided? The thing that I provided is the heat that was received by the system. And the heat that was received by the system is actually this one, the one that is positive in the referential of the system. I'm not going to take that one, the QAB, I'm not going to take it into account, because this is just a heat involved because of the process that I started by the positive one, QCD. So in the beginning, you bring QCD to your system, and then there is a whole mechanism that is going to be created just because of the initialization that you did by bringing the combustion QCD. So QAB is like a consequence of the fact that you created QCD, but what you provide is not QAB, it's QCD. So this is the one that is going to be involved in my equation. So let's go to the equation and let's replace. So for the W cycle, I'm just going to make the addition of all the works that I had. So it's going to be WAB, sorry, plus WBC plus WCG plus WGA. Remember, A is the initial and final state. So that's the summation of all the work of the cycle. And here, what we received is actually QCD, what was received by the cycle. Okay, something interesting. In the beginning, if you remember, we said that when it's isochoric, the work is 0. So actually, half of the transformations that I wrote in the W cycle results are 0. Because BC transformation is isochoric, so this is 0, and the GA transformation is isochoric. So actually, all I need to do now is to replace the results that I had for WAB, WCD, and to replace the result that I had for QCD. And once I do that, then I finish the process. So let's replace. Don't forget the absolute value, as we said. It's important to always keep it here. Over. So QCD is already positive, so I'm not going to specify the absolute value brackets, but I mean, if you want, you can write them too. And here we go. This is the final result of the efficiency for this motor thermal machine that is the Striling cycle. This is a very general example that is like a classic because here we have something that is providing for the operator mechanical energy, and for this purpose the operator had to bring some combustion. So it's like the engine process for this exercise. Obviously, if you have questions, you can write, you can communicate me the questions by email or in the comments, as you want.